Okay, so this is module 3. We are going to look at what are called as colloid polymer mixtures. I'm going to talk a lot about an effect called depletion effects or depletion interactions, and then I will briefly touch upon steric effects towards the end. Okay. So, before we go into colloid polymer mixtures, we could so you will see that a lot of contents from this in this particular module are taken from lecture notes in physics. There is a book or notes dedicated to depletion interactions. If you are interested to know more, you should read up this book. So, the again motivation. Okay, why are polymers added to colloidal dispersions? So, there are you can think about as many motivations as possible. Some of the common ones are to achieve required flow characteristics. Okay, in that sense, they are used as what are called as viscosity modifiers. If you look at a lot of products like paints, for example, or like shampoo, or any material like that, or even the the oral suspensions that people, syrups and all that, right. So, the way they flow out of the bottle, okay, it becomes important. Okay. So, to achieve the right flow properties, people do add certain amount of polymer in a sense that it will affect its viscosity and it will affect the way it comes out of the containers and things like that. We have talked about ceramic processing, wherein you start with a nice dispersion of particles, okay, and then I just mentioned that you can, from that you can actually go to interconnected network called as a gel. I said there is a sol gel transition, and from the gel you can make ceramic materials. Okay. After you take this gel, dry it up, and then you do what is called sintering, right. Now, during drying or during sintering, it's so it's often what happens is that because of the drying induced stresses, these materials they don't hold together. They may lead to, there could be some cracks, there could be there may be defects in the material that you develop. So, so what binders do is they kind of provide the right amount of adhesive forces between the particles. So, you will see a lot of applications where polymers are added as binders in ceramic processing, which could be, which is a method for obtaining porous materials or dense porous materials. So, other motivation to look at polymer addition is you can use polymers for tuning particle interactions. Okay. Again, if you look at a lot of products, like in food, cosmetic or paint industries, you would like to have a product which has a very high shelf life. You want to keep it on the shelf for a year or 2 years. You don't want it to go bad. So, one of the ways of doing that would be to add polymers. When you do that, what you are actually doing is, of course, you are increasing viscosity, which will kind of help you in delaying sedimentation effects, right, because if the things become more viscous, they will take a little longer to settle, right. And on the other hand, you can also tune what is called as particle interactions. I can make the particle interaction either repulsive or attractive depending upon what the product that I am trying to look at. Okay. So, these are some different fields where you will come across polymer colloid mixtures, and it is also known that if you take, like, say, a polymer film, right, and if people are trying to look at its Tg, that is a glass transition temperature of the polymer, it's known that the addition of particles to such a films will also alter the Tg of the film. Okay. So, therefore, there are several cases where you will see that the polymer and the particles they coexist, okay, and therefore, it will be interesting to look at what happens to the interactions between particles when the polymers are present. Okay. These are some examples from literature, again I have taken from the book that I just mentioned. This is a photograph of polystyrene dispersions. This is polystyrene particles, they are spherical particles, okay, and they have 16% particles in volume. Okay. I talked about this phi, right? Phi is the volume fraction. The volume fraction is going to be 0.16 in this case, right? They are in 10 millimolar NaCl. Okay. There is some salt in the system, and everything is at pH 7. Okay. To this, what has been done is they have added a polymer which is called hydroxyethyl cellulose, HEC, okay, and they are added in different weight percentage, okay, which is indicated here, that is 0, 0.15, 0.3, 0.67, okay, and what they have done is they have taken a picture, okay, of the vials which contain these dispersions. Okay. So, the concentration of the particle is the same, pH conditions are same, salt is the same. The only thing that is different in these 4 vials is the presence of polymer, that is it, right. Now, so this is what you see below is the same picture, okay, in which what has been done is all these vials have been slightly tilted. Okay. So, I was mentioning that this is one of the nice way of saying whether something has become gel like or solid like, right. Okay. So, now what they do is they have tilted the vials, and what it does is it demonstrates the difference between rigid colloidal solid liquid and fluid colloidal fluid gas liquid. Okay, maybe let me explain a little bit. So, let us look at this particular vial. Okay. So, what can you say about the bottom phase? See, there are 3 phases, right. Okay, there is one phase here, another phase here. Okay. The bottom phase, this is straight, right. That means it has become gel like. Okay, I can say it is a solid. Okay. What about the next one? It is liquid like, right. So, right, it is liquid like. Okay. The upper one is also liquid like, right. But however, if you look at the liquid, that is this liquid, there is the concentration of the particles there is higher, right, because that is evident from the turbidity, right. Typically, I mean turbidity can mean different things, but if you look at this vial, right, this contains only particles and the salt and and the pH is 7. Okay. So, because this is turbid, so I can say that this is a dispersion of, if you take any latex dispersion of polystyrene particle, it will appear white. Okay. Okay. So, this looks very similar to, I will come back to your question, this looks very similar to this, right. But the only thing, the only difference between the liquid, this liquid and this liquid, these two, is that the concentration of the particle is higher here, higher phi I will say, and is low phi. So, whenever you see a liquid, okay, with a low concentration of particles, you refer to that as a colloidal gas. Okay. The analogy is, if you look at gas like state, right, I mean typically if you look at number of molecules per volume, okay, in a gas like state is going to be lower compared to what you will see for the liquid, and and lower, much lower than what you see for the solids, right. So, in that context, whenever you have a fluid which lower concentration of particles, it is called a colloidal gas. Okay. So, therefore, if you so if you look at the second vial here, so you have a fluid that is actually a colloidal fluid, okay, that is colloidal fluid, and you have a colloidal so let us look at the first one, right. So, the difference between the rigid colloidal solid, right, that is a rigid colloidal solid was this, right, and liquid, okay, colloidal fluid or colloidal liquid, right. And of course, there is also a transition between the gas like region and the liquid like region. Okay. So, this is one way of visually telling something about the phase transitions, right, visually telling something about what has happened to your colloid colloidal solutions after you added a polymer. And if you look at again the third vial, right. So, here they talk about the coexistence of 3 phases, right. Okay, this phase 1, phase 2 and phase 3, right. So, there is a for 0.3 concentration 3 phase coexistence occurs. Okay. Any question? You had a question.
Sir, actually, when we tilt it, it's just like a lamellar classifier.
What is it?
Lamellar classifier, sir.
What do you mean by lamellar classifier?
Yes, sir, it is an instrument, sir. Sir, when we tilt the bottles,
Yes.
so normally in colloidal solution, what happens? The rate of settling is faster in that, sir. So the amount of when it is a straight and when it is tilted one, in the tilted one, the amount of the liquid is still same as in the top one. So I have a doubt in this because this thing we have done in our at our lab scale also. So here the amount of liquid on the top it's still same.
Because you have a same. See, if you look at this vial, right, on an average, I would say that the volume of the fluid in all of them are the same. Now, if I tilt it also, why would the volume be different, right? So, I mean, you are right. I mean, volume of the fluid, whether you take volume of the fluid in this, in this particular vial in this state, or the volume of the fluid in this container, when it is tilted, the volume has to be same, no? Why would there be a difference in the volume? I mean, I don't know in what context you are asking. See, you said, I mean, yeah, the sedimentation, right? Yeah, there's work which shows that if you have sedimentation, carried out in a vial like this versus sedimentation in a vial which is carried like that, there are differences. Okay, that's a different aspect. So what here what you're doing is you're really not looking at sedimentation problem. What the whole idea is, look, I prepared a solution with whatever composition, and I would like to have a rough idea as to what has happened to the contents of the vial, okay, or if something is solidified, if something is remaining as liquid. So, when you want to get a quick kind of a inference, you can just tilt it and then look up what happens, that is all. Yeah.
What is the purpose of HFC here?
HEC.
HEC.
Yeah. So, this is the hydroxy ethyl cellulose is a polymer. Okay. So, this experiment essentially shows that depending upon the concentration of the polymer that you added, okay, your solutions can behave very differently. Okay. And phase separation is occurring, things are becoming gel like here, right. So, this looks like a more or less a solid, right, it's not perfectly flat, but there's a, okay, right. So, yeah, so that's a purpose. So, this is to illustrate that the addition of polymers can significantly change the appearance of the fluid itself, to begin with. Okay. These are some experiments where what is done is, so it's a mixture of polystyrene particles, okay, and a polymer. In this case, it's sodium polyacrylate, okay, and so that's added at different concentrations. So this is okay, same concentration, 185 milligrams, okay, milligrams. Sorry, okay, milligrams per liter. The same concentration of the polymer is added. However, one is taken at 25 minute, the second one is taken at 55 minute. Okay. And if you take a sample like this and if you observe them under microscope, okay, you know, you will see images like this, and you know, these white dots are mostly the particles. Okay. And you know, there is, you can think that there is some kind of a particle clustering, you know, or there is some, you know, phase that occurs, right. So this was to show that there is a macroscopic change in the, you know, the appearance itself, but that is because microscopically also things are changing. Okay. So that is the scale bar is about 10 microliter. If you want to know more, you can just read this up. Okay. And again another example, this is at a higher concentration. So, if you look at these two, right, this was at a very low concentration, 185 milligrams per liter, and this is at, you know, 370 milligrams per liter, which is 25 minutes after the addition. Okay. If you compare this with this, right, this is exactly at the same time, this is at 25 minute, but 185 milligrams per liter concentration, this is at 25 minute, but however at a higher concentration. You can clearly see, you know, the domains look very different. Okay. That means you are able to influence, you know, this domain formation, and that seems to you know, the kinetics of domain formation seems to have increased if you have higher concentration of you know, a polymer. Okay. So, okay. So, this is okay, these are few examples to show that both macroscopically and microscopically the colloid polymer mixtures behave differently from a pure colloidal dispersions. Okay. Now, in general, the addition of polymer can lead to some of these things. Okay. There is fluid demixing. Okay. What I mean by that is you could have you know, a dispersion of particles. Okay. And I could add a little bit of polymers. Okay. Okay. Then this could essentially phase separate, okay, in which there could be, you know, maybe a particles, you know, in one region and maybe polymer in one region, and both of them, you know, could be liquid like. Okay. Both the regions could be liquid. Okay. And the polymers could go to one region, polymer could be, you know, other, so, you know, something like this could happen, right. So, the, you know, the addition of polymer can lead to fluid demixing. It can lead to flocculation. That means if you have particles like this, okay, it can form, you know, aggregates, right. And if the concentration of the particles is high enough, you know, these aggregates could form a space spanning network. That means it could gel. Okay. It could lead to crystallization. Okay. So, say that, you know, the particles are kind of randomly arranged in a dispersion. I add polymer, it could bring in these particles together and it can form, you know, maybe nice hexagonal lattices and things like that, right. And finally, it can also lead to what is called as glass transition. Okay. So, it can, you know, make, so typically when people talk about the behavior of colloids in general, you have sol, then there is gel. Okay. At some concentration it becomes a glass. Okay. Typically at very high concentration, maybe of the order of you know, 55% by volume and more, something like that. Okay.
They can mix properly also, right?
What is it?
They can mix like in a stable form also.
Yeah, it can.
Randomly.
Yeah. Okay, so now what are the parameters that control or that are important to understand the phase behavior of colloid polymer mixtures? Okay. So we looked at, you know, the polymer concentration, right. So we said that, look, the first example that I gave you, this was you know, HEC, right, a polymer, it was at different concentrations. We saw that the polymer concentration does influence the phase behavior. The second parameter that would become important is the size ratio of polymer to the particle. Okay. So, when I what I mean by that is I could have a particle, right, in a dispersion, particles in a dispersion. When I add polymer to it, typically people characterize this polymer, the size of the polymer by a quantity called Rg, okay, the radius of gyration of the polymer. If R is the size of the particle, your Rg by R becomes an important factor. Okay. So, whether the Rg by R is very small or Rg by R is very large. So, depending upon the size ratio of the polymer to the particles becomes important. Okay. And of course, the interactions are important, and when we talk about colloid polymer mixture, we have solvent polymer interaction, particle interaction, and particle polymer interactions, right. So, this would again be depending upon the type of the solvent that you are working with, depending upon the type of the polymer and the type of particle, each of them could be very different. Okay. And of course, temperature, because temperature can both affect the polymer interaction as well as the polymer solvent interactions, right. You could have a condition, or you could have a particular temperature where the polymer would in a crude sense be happy in a solvent. That means it want to stretch out more, or and there could be cases where the polymer does not like to be in a particular fluid at a particular temperature, it would like to coil up. Okay. So, therefore, the temperature becomes important. Of course, the particle concentration, right. So we saw an example where the particle concentration was fixed at 0.16, but however, if I were to have a different concentration of particles, so whatever these changes that we see, they could either be shifted to lower concentration or higher concentration, okay, or a lower polymer concentration, or a higher polymer concentration, depending upon the concentration of particle that you have. Okay. And of course, time, right, that was illustrated in this particular example, where we saw that the same mixture, but if you look at different time, it would microscopically it will be very different, and the same would also be true in terms of the macroscopic behavior as well. Okay. So, we will again, this is a cartoon which tells you something about the size ratio of the polymer to particle. Typically, this people refer to a quantity called Q, okay, which is, as I said, is a ratio of the size of the polymer divided by the size of the particle itself. Okay. You could have a case where Q could be very small. Okay. You could have a case where the Q could be of the order of 1, okay, and Q could be much larger than 1, right. So, when people talk about typically Q less than 1, okay, people use a term called colloid limit. Okay. That means I have added a polymer whose size is much smaller than the size of the particle that I have in the dispersion. Okay. That is what is called as a colloid limit. And when you have the Q is larger than 1, okay, people use a term called protein limit, in which case the size of the polymer that you have added is much larger than the size of the particle itself. Okay. The reason why I think it is called protein limit is because I think when you add, people have used polymer for crystallization of proteins. Okay. That means I have a solution of protein. Okay. Okay. I add a polymer and I would like to crystallize protein out of the solution. Okay. When that happens, the protein molecule sizes of protein molecules are much smaller compared to the size of the polymer that I had. Okay. Therefore, it will invariably fit into Q much larger than 1 or 2 larger than 1 case. Okay. So, therefore, if you have cases where the size of the polymer is much larger than the size of the particle, which is what is depicted in this cartoon, okay, that is what is called a protein limit. Okay. If you have a case where the size of the particles are much larger than the size of the polymer, okay, it is called a colloid limit. Okay. So, whenever you are trying to look at colloid polymer mixture, okay, it is good to identify whether you are working in this regime or this regime. Okay. Depending upon any of these regimes, your colloidal interaction is going to be different, the phase behavior is going to be different. Okay.